Okay, thank you so much for the introduction. And it's a really great pleasure to be here. So thank you so much for the opportunity, Rafael and the other organizers, to be here to present this work for you. So today I'd like to discuss with you basically two results. The first is related to this paper. And the main goal of this talk is trying to convince you that one of the most fundamental experiments in the history of physics, the double-slit experiment, it still has something to teach us. So it still has some new physics related to this very old experiment. And basically what I'm going to try to convince you is that against the standard interpretation, because usually either in classical electrodynamics or Feynman interpretation of double-slit experiments, we usually say that there is no photon, there is no light in the dark spots. So the probability of the photon being in that point is 0. So, and according to the theory we developed here, we proved that in those points we have photons, we have waves, but in a specific state that do not couple to the atoms or to the detectors. So we do not see light in those points, not because there is no light there is no photon there, but because there is no coupling to the detector. You see the difference? So it's a little bit crazy perhaps, but according to the theory developed, this is right. We have been discussing this a lot for the last 3-4 years. So I hope we can convince you that everything here is right. And related to this, there are of course many consequences of these results. And one of them, it's interesting when we deal with thermal states, Gibbs states. Because when we have thermal states, something interesting appears, because in the dark states, we have a coherent state, we have entanglement, but in thermal state, there is no coherence. So in principle, there is no quantum effect. But we can just do a change of basis. And instead of working the bare basis, we can work with the collective base of the modes. And then there are some decompositions on the dark states. And for instance, we have two modes, for instance, in an optical cavity. And a single atom interacts with both modes simultaneously. If both modes are in a thermal state, only half of the energy can be exchanged with the atom. So the other half of the energy remains there in dark states. So there is no way to exchange energy with the atom anymore, and becomes there trapped in somehow. But the result becomes a little bit more surprising when we go to M modes, many modes. And the amount of energy that's trapped in the dark states for all the modes in the thermal states is m-1/m. So that means, for instance, if you have 100 modes, 99% of the energy will be trapped in dark states. So if you put an atom interact with those modes, it will be able to absorb part of the energy. Only 1% of the energy will be absorbed by the atom, and the other rest will be there as a vacuum for the system. So for me, this is very surprising. There are many other consequences. I hope I can convince you that everything is right. Well, when we talk about waves or light, of course, we're trying to understand what is light. This is a very old question. People have been trying to answer this question since the ancient Greeks. So the Greeks were thinking about many things, as you could see in the previous talk. And they were trying to understand how can we see things around us. So in the end, they were trying to understand what is light. So the discussion about what is light comes from there. And we had many discussions about throughout the history. Perhaps the most famous debate was Huygens and Newton. One claiming that, Huygens claiming that light is waves, and Newton claiming that light is particle, and many others. But with the experiment carried out by Thomas Young more than 200 years ago, the double-slit experiment carried out by him, proved that light is indeed waves. And then with Maxwell and many others, we proved that we have wave equations, we have the group velocity, described very well by those equations. So at that time, the particle aspect of light was dead. But this is not the end of history, as you know. With the advent of quantum mechanics, then with Planck, Einstein, the black body radiation, the photoelectric effect explained by Einstein, they introduced again the particle aspect of the light, and then we came up with the concept of photon. And then we have the wave-particle duality and so on, and the origin of the quantum mechanics, and so on. So I'm not going to tell you more about the history, of course, because I guess you know more than me. But let's go to the main point, the double-slit experiment. How can we explain this in classical electrodynamics, or even with Feynman's ideas of wave function describe the photon that cross two slits? For instance, let's take a classical electric field here, a coherent electric field here, can cross the first slit, the second one, and then this light, we have a wave come to this point, another wave come from the other slit to the same point. How can we explain no light in that point? Basically, we calculate the resulting electric field in that point. Then we have the E1 plus E2. When they are out of phase, of course, this results in zero, no light, so no detection, right? This is the way we explain, the classical electrodynamics explain. We can replace this by the total wave function, psi1 plus psi2, and then we have the same description as introduced by Feynman. And then we have the probability of being dot points will be zero. The probability of having a photon those points will be zero. Here, there is no light in those points. And how can we explain this in terms of the detection? To do this, we have to introduce, as Glauber did years ago, many years ago, we had to introduce the interaction between the light and the detector. And the interaction, the most fundamental interaction to describe interaction between light and matter and atoms is given by the dipole interaction. And in this case, it's very clear. If the resulting field is zero, there is no interaction. There is no detection. We do not see light in that point. And this is the way we explain. But now let's move to the quantum version. But not the quantum version by Feynman. The quantum version introduced by Roy Glauber in 1963, so many, many years ago. And then he described all the process in terms of the click of the detector. But to make a click on the detector, what has to happen? We have to introduce the electric field operator, E plus, and the operator that describes the excitation or not of the detector, the sigma plus. And in this case, let's assume that I have just a single photon first. If you have just a single photon, this photon can cross the first slit or the second. If it goes through the first slit, it would be in this direction with a specific wave vector k. So this I named this as mode A. But the same photon can cross the second slit, and in this case with a different wave vector, k prime, and then we named this as mode B. So we have two different modes, mode A and mode B. And according to Glauber, Walls, Scully, many guys that build the quantum optics in the last decades, they state that describes the photon at any point on the screen would be given by this kind of state here. That's quite intuitive because we can have either one photon in mode A, and of course 0 in B, within a specific phase, or 0 in A, in 1 in B. All right? So this is not, as I said, this is not my theory. This is, you can find in many textbooks, and all the theory described by Roy Glauber, the Nobel Prize, by building this quantum theory of the detection, is given by this state here. And then, as I said, the interaction between the modes with the detector can be described by this Hamiltonian here, that basically describes when we have an excitation in the detector, I mean, when I have a click on the detector, we have a photon that is destroyed in the modes. So whenever we have a photon destroyed there, we get an excitation in the detector, and vice versa. Okay? And then the question we had to answer is, having interaction like this, what is the condition for null detection? In classical description, we have to say that the total electric field is 0. But quantum mechanically, we are talking about operators. And then, when we do not see a detection, Rodrigo, when the operator has null eigenvalue. Null eigenvalue means no evolution. There is no change of states of the system, of the detector, and so on. Right? So this is the condition. When the eigenvalues, the eigenstates of the electric field operators has 0 eigenvalue, there is no dynamics. We can put this into the evolution operator, and we'll see exponential of 0. So no evolution, no detection, no click on the detector. Okay? So far so good, so simple, right? And then something changes when we start looking into more detail into this. Because whenever we have just a single mode, imagine that we can control, as many people can do nowadays in superconducting qubits, cavity QED, or in many others, we have just a single mode. If you have just a single mode, the electric field operator is described by the E plus, by the A operator, the annihilation operator of the harmonic oscillator. And then the question, what are the eigenstates of that operator that have 0 eigenvalue? And the answer is trivial. 0, the vacuum. So no energy, no photon, no light. Only when we have no light, no photons, the detector does not accuse, does not do a click. But in the double-slit experiment, we do not have just a single mode. We have at least 2. Or in many slits, we have many modes. And the situation, of course, changes. So in that case, the electric field operator, A plus, has to be replaced by A plus B. The annihilation operator of mode A plus the annihilation operator of mode mode B. And now the same question, what are the eigenstates with null eigenvalue? Of course, the vacuum in both modes is a eigenstate with null eigenvalue. So no click will be done, of course. This is the trivial. But now something interesting appears. We have a huge family of states, collective state, entangled state, completely quantum states that has the same property. That means whenever the modes are in those states, there's no click, there's no detection of light. You see? This is the difference. And of course, in this case, no photon, no energy, but in this case, we have just a single photon shared by 2 modes, 1, 0, minus 0, 1. Sorry. So in this case, we have 1 photon, we have energy, we have light there. It's not because there is no light, no photon. We have photon, we have light, but the interaction with the detector will be 0. Nothing happens. No clicking will happen whenever the photon will be in that state, or in any other here. So psi n 0, all of them, we have photons, but with 0 coupling, effective coupling to the detector, to the matter, to the atoms on the screen. And this is why we do not see light. This is the states we called dark state. Because of that property, because they do not interact with the detector, so no light detection would be seen in that case. Let's go to the other point. Try to explain the bright spots in the double-slit experiment. Again, if we have any photons and we have just a single mode, there is an exchange of energy between the detector, the atom, and the mode. And this will be given by a fundamental coupling G and the square root of n. This n is the number of photons. So if you have just a single mode with any photons, the exchange rate of energy between the modes and the atom or the detector will be enhanced by the number of photons we have there. That's quite normal. But let's go to two modes. When we have two modes, there are some specific states I call psi nn that has a coupling enhanced by a factor 2. This factor 2 comes from the collective effect of the modes. So in the end, this is the direction I would like to bring you. We see more light in the bright spot, not because we have more photons there, but because the coupling is enhanced. You see, the amount of photons will be the same, as I will show you, in both, in dark and bright spots. But in one case, the effective coupling is 0. In the other case, the effective coupling is enhanced in such a way that we see more light scattered, but not because there are more photons there. So it's very different. And in fact, there are a family of those states they present stronger coupling. And if you compare to the previous ones, just change the phase. Before the dark was 1, 0 minus 0, 1. And now we have 1, 0 plus 0, 1. All of those states, they are very similar to the previous ones, but the phase changed. And now all of them has an enhancement in the coupling. So the coupling is not square root of n only, but there is the square root of 2, because we have two modes. Later on, we'll see that when we have m modes, this coupling is enhanced by m. So let's go by step by step. So those states are the ones I call bright states. Rodrigo or someone, please tell me the time. I still have a lot. I saw. Okay, good. But I usually start talking too much, explaining too many details. Okay. What's happening here, in the end, is quite simple. So I have in my office a small car like this. So I have two pendulums. And we can put this pendulum to oscillate in a symmetric way. When we do this, there is a coupling to the center of mass of the car. And then the car starts moving to the right, to the left. So there is this coupling. But if you put the same pendulums, the same coupled oscillators, oscillating out of phase, that are the anti-symmetric state, there is no coupling to the center of mass. And this is very intuitive for us. It helps us a lot because in both cases, we have energy. We have oscillation in the modes. But in this case, there is no coupling to the center of mass. So if you are looking at just the center of mass motion, you wouldn't see motion. You wouldn't detect photons. But whenever the modes are oscillating in a symmetric way, there's the coupling, and then we would see the motion. We would see the light. So this happens already in classical physics. But the difference is, of course, in the quantum version, we have a much richer case. We have much more states, a plenty of states, and then many other things can happen. So, but can indeed this theory explain the pattern we see in the double slit experiment? As I told you, the state that describes the photon, in the single photon case, on the screen here, is given by this state as I showed you before, according to Glaub and Boas and many other people. Well, there is a difference of phase here in both. And what happens? Whenever we have the difference of phase 2n pi, we have this state, that are the detectable one. So indeed, in the bright spots, according to standard interpretation of interference in double slit experiment, we have exactly the bright states. And of course, in the destructive points, when the difference of phase are given by this, then we have in the minima points, we have exactly the dark states. This is why we do not see light in those points. But you see, if you calculate the average number of photons in this state, we have 1. In this state, we have 1 as well. So the photon goes to both points. But here, in the bright spots, we have a detectable state. In the dark spots, we have an undetectable state. So everything here is for just a single photon. All this theory can be extended to many, many photons, to coherent state. As we can do easily with a laser point here, we can do this experiment. I did a lot of this experiment in the last month, trying to find many other things. So let's assume that we have a coherent state, so a superposition of many, many, many photons. And if you have, in this case, a coherent state crossing the first slit, a coherent state crossing the second one, we would have a state like this. That depends on the difference of phase, of course. And what is interesting here is, whenever we have the difference of phase 12 pi, we have two coherent states in phase. According to classical interpretation, we'd say we have constructive interference because they are in phase. But according to our theory, we have the composition on only psi n n. Psi n n are only bright states that couples to the detector. This is why we see light in those points. On the other hand, for difference of phase 12 plus 1 pi, alpha minus alpha, the standard destructive interference, but in fact it's not because we do not have light there. We have, but the photons there are only projected onto psi n 0, the dark states. So we have only the composition in dark states, and this is why we do not see light. So you see, the photons are there again, but in a state that cannot interact with the detector, with the matter, the screen we have there. Well, everything I showed you, of course, is very similar to, I can explain the interference, the pattern we see in double-slit experiment in a different way. And in fact, if you calculate the resulting electric field in any kind of dark states, the resulting electric field is 0. So this agrees with the standard interpretation, standard classical explanation of interference. On the other hand, all the bright states have no null resulting electric field. So this is why. So there is a match, perfect match between. But the question, there is something new that this theory can bring to us. This question was, Gerhard came with this question to me, the other author of this paper, and he was telling us also, everything that we are explaining with this new theory, we can explain with classical theory. There's no difference. So what is new? The natural question for that. And then I started to think about this, and then I came with this state I called epsilon state. That is the first mode in 0 plus 1 photon, the second mode in 0 minus 1 photon. And then if you calculate the resulting electric field for that state is 0. Oh, that's nice, because 0 means classically no detection, no light would be seen when we prepare modes in that state. But then, when we calculate the interaction with the detector, the Hamiltonian has no, this is not a null eigenstate of the Hamiltonian. That means if you prepare the modes in that state, we would see some excitation of the detector. We would see some click. And why we see click? How can we explain in terms of the theory I explained to you? Because that state has project onto vacuum, the dark state 1, 0, the dark state 2, 0, and 2, 2. The last one is a bright state. So that epsilon state has a projection onto the bright subspace. And this is why we would see light. You see? Well, there are many consequences of these results. One of them that I like a lot for me, perhaps the most important consequence of this paper, of these results, is demystifying the role of the observing double-slit experiment. Why? Because so far, we usually say the following. If you send light, for instance, a single photon here, we would have this interference pattern here. But if you include a path detection, but this path detection has to be seen in the following way. It's a detector that can tell us in which slit the photon has crossed, but the detector is so tiny that it cannot introduce any momentum to the photon. In other words, cannot change the path of the photon. That means if the photon is going to a dark spot, or I mean, in a bright spot, the photon remains going to the bright spot. You see? But then how I could explain the presence of the observer changing the path? For me, this is so magic. The standard interpretation of quantum mechanics for me is kind of magic, because without introducing any momentum to the photon, the photon starts going to dark spots that in principle, the photon should not go there. So magically, the photon appears in the dark spots. Of course, we interpreted this in terms of the coherence, we kill the coherence of the superposition, then we have, but it does not explain the momentum changing. Because how the momentum changes in this case without introducing any momentum. This is surprising for me. This is standard interpretation. But how my theory, this theory I explained to you, solves this problem? Let's look into detail here. In the bright spots, we have bright states. 1, 0, plus 0, 1. In the dark points, we have dark states. But according to the theory, the photon is always going to bright and dark spots. But when the photon goes to the dark spots, it's in that state that is indetectable. So it goes there, but we cannot detect. And what happens when we introduce the detector? When we introduce the detector, as Gay had showed many years ago in an experiment, appears an entanglement between observer and the photons. Oops, sorry. And the modes. And this destroys the coherence and so on. But according to this theory, what happens here? When we trace over the mode variables, we end up with a mixed state. So the bright state psi 1, 1 is reduced to that mixed state. In the dark spots, the presence of the observer, when we trace over the variables of the observer, we end up with the same mixed state. So the photon now has projections. This state has projection into the bright state and then can be detected. But you see, there is no change in the momentum of the photon. The photon would be going there always. The presence of the observer just destroyed the coherence of that state, making some appearance in the bright state projection. Okay? Well, another important question, can we observe such states? Can we do experiment with this and see? I have been trying to do this with light. That's really difficult because it's difficult to control the symmetry of the interaction between the modes and the light, and the atom or the detector. But there are other systems that can mimic this easily. For instance, in trapped ions. In trapped ions, we have the same dynamics, and then we can have one vibrational mode here, another vibrational mode there, and then we have basically the same system. It's not the same dynamics. And then we did this experiment together with people from Stockholm, Professor Marcus Heinrich, and the results confirm exactly, match perfectly the theory. I'm not going into details here, but all the results I showed you, we could observe there, and we could see that indeed, everything happens in the lab. I have time? Okay. What? Huh? It's already? Okay. So very briefly, extending this to any modes, what happens? When we have many modes, of course we have to deal with this, not just 1, 2, but now M, and then there is an enhancement in the coupling. So the main difference is this one. For 2 modes, we have one bright and one dark state. For it doesn't matter how many photons we have, we always have 1 and 1. But for M modes, there is just a single bright state and M-1 dark state. So there is a predominance of dark states. And this is very interesting because if you have a general state, the vast majority of the photons will be in dark states that do not interact with the. So, and the idea is in that paper, and if you have the, let's assume that we have the modes, all of them in thermal states, so no coherence, no quantum effect in principle. But what's happening, the most important is here. There is one symmetric mode and M-1 anti-symmetric modes, orthogonal to the symmetric one. And the most important is this. The interaction between the modes and one atom, if you put one atom interact with all of them together simultaneously, they interact only with the symmetric mode. That means if you share the energy in M modes equally, and we work in the collective basis, only the symmetric one will be able to exchange energy. All the others, the composition, the anti-symmetric modes, will not be able to exchange energy with this atom or with this detector. So again, does not need to go. And this is the final result. The energy in the symmetric mode will be proportional to the mean number of thermal photons in a single mode. And the energy in the anti-symmetric modes goes to M-1. So the vast majority of the energy in thermal states, so we have many modes, M modes, all of them in thermal states, the vast majority of the energy will be in dark state that do not interact with the atom. And then we carried out some simulations. If you have just a single mode interacting with a single atom, and this atom is catching light, I had to finish, yeah. And what happens? All the energy can be absorbed by the atom. So the fraction of energy goes to 0 for a single mode. For 2 modes, half of the energy remains trapped there. For 3, 2/3, and for 190%, 99% of the energy remain trapped in the dark states. Okay. Well, let's finish here. There are important discussion here, but I'll skip it. Sorry for that. Thank you so much.
Thanks for the really nice talk. I think we don't have time for question time, so.
Yeah, can be this one.
Maybe one question while the computer. Okay, one question in the meanwhile.